So hi everyone, my name is Keiran. I'm a PhD student at the University of Leeds. I'm in my 4th year now, and I'm going to talk a little bit about some work I'm doing on estimating categorical variables using the Ensemble Kalman Filter. Let me do that. There we go. So I thought I'd start off by talking a little bit about some of the previous work that I've done. So like Nick said, we've been doing some work on modeling pedestrians in the Grand Central Terminal. We've been using this station sim model, and we've been calibrating the agent speed parameters using real data. And as Nick mentioned, we've been running experiments using synthetic data. And we're assimilating data with a constant period. So every, let's say, 50 time steps, 20 time steps, whatever it might be. I thought it might be worth just going over how we're generating synthetic data before we get into anything. So we're taking an instance of the model as a ground truth, and then taking copies of this ground truth model, and those will be our ensemble members for our Ensemble Kalman Filter. And these members inherit stuff like agent entrance gates, agent exit gates, and agent speed parameters. And then we're generating synthetic data by adding some Gaussian noise to the ground truth state that we're getting from the ground truth model. And then we've gone ahead and applied the ENKF, and we can see when we run things, each of these dots pertains to an individual agent. So if we, for example, zoom in here, we've got an observational agent 0. We've got the ground truth model, where the ground truth model has agent 0, and then we've got a posterior and a prior. So the model state prior to data assimilation and the model state after data assimilation. What we can also do is have a baseline. So a baseline here would be another version of the model that would be running without any information fed in by data assimilation. And we can see in the case of almost every agent that the data assimilation scheme means that we outperform baseline pretty much every time. So you can see that as they move along, the prior and posterior roughly match the ground truth in a lot of cases, which is quite nice. But there's a problem here, which I think Nick has kind of outlined somewhat already. And it's basically, we're assuming some knowledge of the system, which we probably don't really have access to. So in the current scenario that I'm simulating, we've got this bunch of known variables, which is the entrance gate, the entrance time, the speed, the exit gate, and we've got an observed variable, so the agent XY location. But in reality, we don't have access to some of those known variables, or the things we think are known. So in reality, we would probably have access to an entrance gate and an entrance time, and we'd be able to observe the agent XY location, but we wouldn't know about the agent speed parameters or the exit gate. So let's have a think about what our model looks like. So if we have the whole ensemble, the ensemble itself is a collection of model states from model 0 up to model n. So we've got n copies of the model. And each model state is a collection of agent states. So you've got, let's say, m agents, so agent 0 up to agent m within each model state. And each of those model states, so each of those agent states has an XY location. So how do we change this? How do we fix this such that we can infer some of these unknown variables? So like the speed or the exit gates. So the work that I'm looking at is looking specifically at identifying this exit gate. And so we're going to look at what we can do to change this kind of model state to make that work. And this is something that I'm now sort of thinking about at the moment and planning to do over the next few months. So I've got some ideas of what I would like to do and how I'd like to approach this. So I've kind of divided them into two groups. One is estimating the gates inside the model state vector, and the other is estimating the gates outside the model state vector. So if we're doing it inside the model state vector, then one of the ideas or two of the ideas I had were to just estimate the gate number. So we'd allocate numbers to each of the gates and estimate those numbers. And the second is to estimate a score for each gate. And then if we're doing outside, then we could train some kind of model based on the agent's XY coordinate history and then use that. I'm going to kind of go into a bit more detail on how I think that these would work. So if we're estimating the gates inside the state vector and we're doing it on this kind of estimating gate number idea, so we'd say we're going to allocate a gate number to each of the gates in the environment. And then we're going to change our model state such that it has, for each agent, originally it had an X and Y location, and we're going to add a gate number. So X and Y location will be two continuous variables in the XY plane, and gate number will be a categorical variable or a discrete numerical variable ranging 0 through 9. We've got 10 gates. So there's going to be some problems here. So the Ensemble Kalman filter might do some estimating, and it might come back and it might say to us, well, we're estimating the gate number for agent 3 is gate 1.7. Now, in our kind of gate system, that's not really very meaningful because our gates are all integer values. So what can we do about this? So I propose that we use some clock-based rounding. So there's two issues to deal with here. First of all, the idea that we've got categorical variables and our Ensemble Kalman filter might return non-integer numbers, in which case we can just round to the nearest number. And the second issue is that of rounding. So what I might do is I might go to, so we had this image of the gates. So the gates are in blue around this red environment. And let's say we allocate number 0 to the top left, 1 to the top right, as follow around like that. And then the Ensemble Kalman filter said, well, I'm suggesting that this agent is headed to gate 9.7. Well, then if we round it up, it would be rounding up to 10. So we're going to use some clock-based arithmetic and round to 0 because we're taking 10 mod 10, which would be 0. So that would be one idea. The second idea that I had for this would be to just estimate a score for each gate. So again, we'd have this original model state, which was X and Y locations for each agent, and we'd add a score for each of the gates, for each of the agents. So here we'd say Gij refers to the jth gate for the ith agent, and that would be a score pertaining to the jth gate for the ith agent. So for example, G75 would be the score for the 5th gate for the 7th agent. And then what we'd do is we would get, at each data assimilation point, we'd get the score, each of those scores, and identify the maximum, and then identify the gate that had the maximum score. So an alternative idea that I had was to estimate the gates outside the state vector. So one thing that Nick's mentioned, and you will notice, is that the agents all move in a largely linear fashion. And so we can kind of use some of this knowledge about the motion of the agents to perhaps choose how we do this. So again, we'd have our state vector for a model, and we'd say, well, our pedestrian motion is mostly linear. So what we could do is we could fit a linear model to the previous ensemble states for each of the agents, and then propagate the model forward to an intersection point with the environment boundary. We could calculate the distance between this intersection and each of the gates, and then assign a gate, or assign the gate to which is closest to this point of intersection to that agent. So I think I'm probably going to round up around now. So at the moment, like I said, the current state we're doing is, well, we've got this ENKF. It improves the accuracy with which Station Sim simulates the pedestrian motion. It outperforms our baseline. The problem is that we're assuming some prior knowledge here that's probably not reasonable. So we have these kinds of issues around not knowing the gate number for each of the agents, which is a categorical. We don't know this necessarily the speed. And so I've proposed a few solutions, which I'll be probably looking into over the next few months, which is estimating the gate numbers, estimating for scores for each of the gates, or perhaps training a model based on the agent's XY coordinate history. Some other potential avenues that might look at, like I said, speed is not something that we necessarily know. We could also include that in the estimation. And I'd also be looking eventually to start using some real observations instead of synthetic data for the data simulation.